Hello, good evening. Welcome to the credit card fraud detection project. This is a small demo video of the implementation of the project. Let me just briefly give you how this project can be implemented. The documentation is attached for you to go through the entire project. So to run this project, what are we going to do? I'm just open the README file for your reference. I'll just run you through this. So first we create a Python environment. So this project was designed using the 3.9.18 Python files. So we can simply create this virtual environment, conda create minus p venv python equal to 3.9.18 and give the dash y for accepting the commands. So this will create the conda environment and then we activate the conda environment. I've actually opened my bash terminal and I've activated the conda environment here. This project is better run in the bash terminal because we need to export some variables. I will deal about this in the end. So to simply activate the environment in our bash environment, we can just say source activate the environment. In my case, it is VNV. I'm sorry, there's a spelling mistake. VNV. My source is already activated. So once the source is activated, we can install the requirements by typing this command pip install -r requirement.txt. The requirements are listed here for your reference. So we use pandas, numpy, seaborn, flask, and other important libraries, which is important for the project. So that will be installed next. I've already installed. So I have enabled the dash e dot parameter so that it installs all these project files also as components within our environment. So I've already done that. So you can go through this. These are the preliminary steps we need to do. Then I'm just briefly explaining to you how before calling the training pipeline, I'm explaining to you how the training process is going to happen in our project. So if we just go into our components, we have different components here. The first component we start with is the data ingestion component. Let me just briefly give you an overview. So what this component is doing is that it is making test.csv, train.csv, and raw.csv artifacts in our artifacts folder. So this is our artifacts folder where all the files, including our model, preprocessor, data validator, all are being stored here. So this data ingestion pipeline or the data ingestion component is going to deal with drawing the data and storing them as these three variables, that is train.csv, test.csv, and raw.csv. So how this is being done? So we have integrated YAML files into our project. So what this is doing is, so once this pipeline is called, so it will actually the data we have downloaded and kept in our notebook folder. This is the data here. So it is going to read the data from the notebook folder. Then it is going to split the data into X and Y, that is our independent and dependent features. It is also going to see our schema.yaml file. So this schema.yaml file, let me just briefly explain it. So in schema.yaml file, we have declared all the data types of our columns in a methodical fashion, and also we have given the name of our target column. So it is going to read that, and it's going to based on that, it is going to divide the dependent and independent features into X and Y variables. Since there is imbalanced classes in our data set, we are using the IMB learn combine SMOT dot TOMEK. This actually balances the difference in classes in our target variable. So our target variable is 1 and 0. That is the aim of our experiment, actually, to see whether the credit card holder is going to be defaulting for the next month, or is he going to pay for the next month. Okay. So it then concatenates the X and Y, then it splits it using the train test split with a test size of 0.3, that is 30%. And it divides it to train and test, and the train and test set is being stored in our artifacts folder. That is what it is doing, and it is returning our train path and our test path as the return variables. Okay, so this is the data ingestion part. Then actually what happens next is we are going to call the data validation, because we want to validate our data. So what we do is we call the data validation, and the data validation actually takes up the same thing. It is just looking at the raw CSV file and it is generating a data validation.txt. This is the file it is generating if all the columns and the schema is met with respect to the raw.csv file. Okay, and as for this we are feeding our raw.csv, train.csv, and test.csv files as our variables into this class. Okay. So again, data validation goes through the same process. It takes up the schema, reads the columns in the schema. Then for each file in our artifacts folder, that is all these three files, raw, test, and train, it goes through each of the columns and verifies if each of the columns has the corresponding data types, and also if all the files, all these three files are there in our artifacts folder. If it is there, it's going to return as it return as yes. So if we open this file, it is showing here, it is going to return as true, sorry. And if it is not there or if the data types are different, it's going to return as false. So this is the main function of the data validation component. So it's going to return true or false. If true, if all our data is validated and all the columns are present, and false if these standards are not met. That is what the data validation does. Next is the data transformation. So data transformation basically picks up from where the data validator leaves. So it again takes up the columns. It then divides the columns into categorical and numerical columns. Then we have devised this numerical and categorical pipelines. So based on that, it is sent into a preprocessor and a column transformer is called to transform the numerical pipeline. So the numerical pipeline basically it goes through a simple imputer wherein we use the median as the strategy and it uses standard scaler to scale the values. In categorical pipeline, again simple imputer used, but here the mode is or the most frequent is used as the simple imputation technique. Then we one hot encode the categorical variables and then again we use a standard scaler with mean false for the categorical pipeline. So this is what the preprocessor is doing. So this preprocessor calls in, takes in the train data and test data. It then separates out the respected columns. Then it so here we have done some feature engineering a little bit. So here what we have done is we have modified the features a little bit. So sex was 1 and 2, 1 for male and female if I remember, 2 for female if I remember correctly. That is scaled down to 0 and 1. And also we have reduced the categories. Some of the categories we have reduced it. This is mentioned in the documentation for further reference. So this some feature engineering is being done here. And then after the feature engineering, we are then separating out the train and test data. Independently, we are doing fit transform on the train data frame and just transform on the test data frame. And then it is going to return us the preprocessor object, the file path of the preprocessor object, and it is also going to return us the arrays, different arrays, that is train array and the test array. So these three things, the train array, test array, and the preprocessor object path is returned to us from the data transformation. And finally, the model trainer. The model trainer is nothing. The model we converged on was random forest because it gave the highest accuracy to our experiments. So random forest is called here. So the parameters from the random forest are mentioned in this params.yaml file. I just opened that for the perusal. Params.yaml file. So these are the three parameters for the random forest. That is n estimator equals 300, max features equals square root, and criterion equals guinea was provided to that. So that goes into our model trainer. So it picks up from that params.yaml model train. That params are passed on to our model. So the x and y train, x test, y test, which was stored here. So which was stored here, that is from the test and train CSV, it is taken out. I'm sorry, the data transformation pipeline returns these arrays, actually train and test arrays. So from the train and test arrays, the x train, x test, y train, y test are separated, and the model then tries to fit that and calculates the accuracy, and the model trainer returns us the accuracy at the end of that particular call. So that's the model trainer, and we have also integrated the ML flow pipeline into this model. So we have imported the ML flow and we have set a tracking URI. So this is the tracking URI for the ML flow. I will demonstrate that in the DAXhub repository. So this is the brief outline of our project, how the model is being trained. And then apart from this, we have a prediction pipeline. So let me just open the prediction pipeline. So prediction pipeline is very simple. It calls in that preprocessor and the model and the preprocessor it is called. So it takes in the data, applies that particular preprocessing, applies that particular model, and then it predicts the given data, and that returns the prediction. This is the prediction pipeline. This is about it. And all the artifacts are generated here, that the model and preprocessor are being stored within the artifacts folder. So first I will demonstrate the artifacts, how it is being created. I'll delete this artifacts folder here. Let me just run the uh, training pipeline. Okay. So I've activated my environment. I'm going to call the training pipeline now. Let's see how it works. So I'm going to call Python src pipelines and training pipeline. I'm calling this. Let's see how it works. So we have implemented all the logs and everything. The logs are being output into the console. You can definitely have a look at the console. Now the the data ingestion pipeline is first called. It goes in, it then ingests all the data and then stores it in our artifacts folder. It's being created here for your reference. Then the data validation goes in, checks for all the data validations. If it is true, the data validation status is returned as true. Then it goes to then it calls the next pipeline, that is transformation stage. The transformation stage is now called, and then this is the input data for our transformation stage. Then it pre-processes the data, applies the preprocessor object, transforms the data, and then again stores it in our artifacts. Then finally there was an error here. I'll just explain to you why the error occurred. We have not exported the variables. So for MLflow integration, we need the variables. So that is again mentioned in our README file. Let me just show it to you. README file is here itself. So we need to export these two variables. That is why I am demonstrating in the bash terminal. Let me just 1 second. Yeah, I'm just exporting these variables, and I need this variable as well. Sorry, let me just copy this. There it goes. Let me just run the pipeline again. We should be able to see that. So it will start from the beginning. Let me just see how the model goes. Yeah, so random forest is initiated now. So the training takes a little bit time because of ML flows actually, and random forest itself takes some time for training. I'll just briefly pause the video here. I will come back to you once the model gets trained. So you can see that the model has finished training for us. So you can see that it has returned an accuracy of 83.34%. And this was the highest accuracy we could achieve in this project with multiple cross validations and grid searching. And we have incorporated that into the project. So the model training has completed, and the model is stored in the artifacts folder as model.pkl. So you can see that here, it is stored in the model.pkl, and it ends the training. So what file I've called is actually this training pipeline. So I've just integrated all the different components like data ingestion, data validation, transformation, and model trainer. This is the pipeline which I called. That is the model training which has happened now. So this was the model training. This is the first part of our project where the model needs to be trained for us. That's the time when it creates the models and the preprocessor pickle, which is needed for our prediction pipeline as well. So that is here. And regarding MLflow, I'm just demonstrating. So this project was actually synced into DAX Hub. This is the project here. And since we gave the tracking URI, we can track it from our MLflow. I'll just go into the MLflow UI option here. So I had deleted all my previous experiments. This is the first experiment being created here because I just ran the training pipeline. We can go through this and just take a look at the MLflow. You can see that everything is logged here about the model, all the input and output details. The ML model is again logged here. Conda.yaml is created. Model.pickle, you can see 217.16 MB file is here. Python YAML, all the requirements are noted here. Estimator is here. So we can see that n estimator is 300, random status 2. This is our confusion matrix. So you can see the predicted and true labels from here. This is the precision recall curve, which is good, and this is the ROC curve. You can see that the true and the false positive rates, they converge at the left top corner, which is also good for our project. And all the metrics, the accuracy score as well as the training loss, all are logged here. With multiple experiments, definitely we can have a comparator and see which experiment performed better. So this is a kind of model tracking we have implemented in our project. Now comes the prediction part. I will now focus on demonstrating the prediction part. So for the prediction part, this prediction pipeline, we have built it on the Streamlit application. So I'm just the Streamlit file. I'll just show it to you how it is. We have integrated in this application.py. So we have imported Streamlit and we have created a landing page and we have created an image, and what we have done is we have created a folder for uploading the CSV file. It will take the CSV files, apply pre-processing, call the model, do the prediction, and return the predictions. It will return if the prediction is 0, it will return as loyal, that is the loyal customer, and if it is 1, it will returns as the defaulter. This is what the Streamlit app is doing. So I'm just demoing this particular application right now. Okay, so I'll just call, we have mentioned this in the README file. I'll just copy those commands. So streamlit run application.py. Okay, so streamlit run application.py. If the artifacts are created, this should run without any problem. So this has opened in my browser. Now the landing page is opening. So this is my landing page. So it says the credit card fraud detection project. This is a simple image we have added. So this is where we need to upload the CSV file. So for this, I have already prepared a small CSV file. I've just taken it from the train data sets itself. So what I've done here, I've just copied the train data set and I've just removed the last column, which is the defaulter column, the target column I've just removed, and I've just taken 10 entries. Yeah, I've taken 10 entries, sorry, 9 entries with one as the column names, 9 entries. So I'm going to upload this file here, and let's see what happens. I'll take this and I will drop it here. Yeah, so you can see here that it has uploaded the data. We can have a look at the data here. So this is the entire data which is there. And then it has returned the predictions for our data. How the predictions are returned, so you can see the ID column, it has taken the ID here, and then it has written the predictions as defaulter or lawyer. So this is the entire project. This is how the prediction works for this particular project. So it returns it as either defaulter or loyal. This goes on. So we can have multiple CSV files. We can have plenty of CSV files. We can give it to this project and it will return to us with IDs. So we can easily, with IDs, we can match who's defaulter and who's loyal. With 83.3% accuracy, we can estimate this particular outcome. That's the entire project. Just stop the project now. Okay. So we have also integrated the Docker file, and we have made a Docker image. So this is the Docker file which is included. A Docker image has already been implemented, and this will be included in the project itself. So I'll show you where the Docker image is. Let me just open Docker. Just logging into my Docker hub to show you the Docker file. So yeah, this is the Docker file. This URL will be included in the README file for reference. Anyone who wants to use this project can use this Docker. We can go to builds, I think. Yeah, sorry, public view, it gives the public. So yeah, this is the Docker pull link. So you can use this Docker pull link and you can definitely deploy it anywhere, AWS, Azure, GCP, we can deploy it anywhere. Same thing works. So this Docker image has everything inside it. I will show you the overview. So let me just open the Docker file. So this Docker image is nothing but it is running on Python 3.8 Slim Buster. It uses exposes this port, that is 8501. This is the default port for the Streamlit. It then installs the updates for the Ubuntu server, and it does whatever is required here. Then it creates an app directory, copies the project files into this app directory. Then it installs the requirements and it runs the Streamlit application. That's what again opens us this that particular landing page which we saw. So that's the entire project. I hope you liked it. Thank you.